Okay, let's work pathways problem 7.39. I've chosen this problem because it demonstrates two different concepts that for the purposes of this problem we can group together, and it shows an example calculation for each. Okay, 739 reads there's a 232-pound fullback that's running at 19.8 plus or minus 0.1 miles per hour. We want to know what is this fullback's so-called deBroglie wavelength, and what is the uncertainty in his position. All right, this question probably reads pretty strange to you, okay? Thinking about macroscopic objects like football players in this particular case, right? However, at the microscopic level, these concepts play a much, much bigger role. The first concept in part A is that of something called the deBroglie wavelength. The idea here, in a nutshell, is that all matter, all material that has a mass, exhibits some wave-like properties. And the deBroglie wavelength allows us to actually compute what the wavelength of matter essentially is. Now, in this particular problem, we are going to compute the wavelength of this 232-pound fullback, which I think we're going to find is pretty darn small. Vanishingly small. We probably will never even notice that, but the theory behind this is that all matter exhibits some wave-like properties. Okay, so let's just kind of dive in, I guess, to this first one, and then we'll come back to the second one. Okay, now the equation that we need to use to compute the deBroglie wavelength of anything is listed here on the board. The deBroglie wavelength is this term right here, normal wavelength sign, and it's equal to h, the Planck's constant. Planck's constant has a value of 6.62 times 10 to the minus 34. Now in the past I've been using joule seconds for that. I'm going to change the unit now just so that you can see that the units jive a little bit better to more fundamental SI units, which are going to be kilogram meters squared per second in this case, okay? All right, so that's the Planck constant. Now what I'm going to do is I'm going to divide that h by two variables that are multiplied by each other. M is the mass of the object that we're talking about. Now, to make the units work, it's very important that we use kilogram units. So whenever you use this equation for the deBroglie wavelength, there also this uncertainty bit we're going to get to in a second. You want to use kilogram units. Kilogram units will be very important. Okay, keep that in mind. And this other term, mu, is the velocity of the object. So it turns out the two things that are important for determining this deBroglie wavelength are the velocity and the mass of the object. We multiply them together in the denominator. Now the problem that we have in this problem is that the units need to be meters per second for velocity and kilograms for mass. Now I look back at the problem, I'm told about the person's velocity, I'm told about his weight, but it's not in kilogram units and it's not in meters per second. So the first thing that I need to do before I do anything else is convert, okay? I need to convert my 232 pounds into kilograms. So I'm going 2 kilograms away from pounds. It just so happens, if I look up the conversion factor, 1 pound, physically equivalent to 0.4535 kilograms, which allows us to quickly determine that this football player's mass is 105.233 kilograms. Right? So 105.233 kilograms goes there. Now likewise, we were told his velocity is 19.8 miles per hour, mph. We need meters per second, so we need to convert. mph undesired, meters per second, velocity units desired. 1 mile per hour, as it turns out, is physically equivalent to 0.447 meters per second. Miles per hour cancel, and we quickly figure out that 8.851 meters per second is this football player's velocity. So boy, he's moving pretty quick, right? 8.8 meters per second, almost 20 miles per hour. So I hope when we run into him, his deBroglie wavelength has him in a node, right? So it's funny deBroglie wavelength humor, I guess. Wave humor there. All right, so anyway, moving on, we've now successfully computed his mass in kilograms and his velocity in meters per second. So I'm going to erase that since we put the numbers in the equation already. We just need to plug and chug at this point, basically. So we put the 105 in, we put the 8.85 in, and we compute this football player's deBroglie wavelength to be 7.107 times 10 to the minus 37 meters. So 7.1 times 10 to the 37th, the negative 37 meters. Now think about the magnitude of that measurement for a second. Is that a big number or a small number? This is a vanishingly small number. You never have any chance of measuring that. It's so small, right? I mean, even when you think about atoms, they're on the order of 10 to the minus 12 meter or something of the sort. This is vanishingly small compared to that, okay? So macroscopic objects that tend to have very large or significant masses, doesn't even have to be very large masses. I mean, we could talk about an orange or a baseball, just anything that's familiar in our everyday life. If they've got significant mass, typically speaking, their deBroglie wavelengths are really, really, really small. We don't ever notice that in our everyday life. But think about the case where we're talking about subatomic particles, maybe protons, neutrons, electrons. Those guys have tiny, 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 tiny masses. All right? And as a consequence of that, their deBroglie wavelengths may, in some cases, get to the point where it's significant for their behavior. All right? So that's the difference. So this is a macroscopic object, and this deBroglie wavelength is so minuscule as to be unimportant. But for subatomic particles, sometimes this can be an important factor, okay? All right, so that's part A of this problem, computing deBroglie wavelength. Let's move on to part B, which is about the uncertainty in this player's position, okay? All right, now this is again going to be a little bit confusing because it's kind of more of a theoretical physics thing. You say, well, uncertainty is position. The guy's right here running at me, right? How can it be uncertain, right? Well, what this portion of the problem is getting at is something called the Heisenberg uncertainty principle, which is covered in this particular chapter. And again, this principle is largely unimportant in our daily lives with macroscopic objects like football players, baseballs, oranges, what have you, right? But at a microscopic level, at a level of subatomic particles, this principle can be really quite important because it limits how we can describe the electron's behavior in the atom, basically. How well or how precise we can describe where electrons are in our atoms, right? And that's why it's considered in this particular chapter, because it leads to the realization that we need to treat electrons in atoms from a probabilistic perspective and not necessarily a discrete perspective, a perspective where we know exactly where the electron's at every moment in time. In fact, we don't. We just know the probability of where electrons may end up, okay? And the reason why that is ultimately comes back to this uncertainty principle. Now, mathematically, what the uncertainty principle says is stated right here on the board, okay? It basically says that the product of the uncertainty in the position and the particle's momentum. So for any particle that's in motion, right, the particle has a certain position in space, and if it's got a velocity or speed, it's got a momentum associated with it because mass of the particle times the velocity is the momentum, okay? So these delta x and delta u terms, those are the uncertainty in the position and the uncertainty in the velocity. So if you take the product of the second one, the velocity times the mass, right, that is the uncertainty in our momentum, and this one is the uncertainty, the position of the particle. So that the principle says that the product of those two uncertainties has got to be greater than or equal to the Planck's constant divided by 4 pi. All right, so basically what that means for us is that we can't really simultaneously know to a large degree of certainty where a particular particle is and simultaneously know its momentum. And again, this is most important for particles that have a very, very small mass, okay? All right, now let's see if we can use this principle quantitatively to actually compute what the uncertainty in position of this fullback is based upon this principle, okay? And actually not too difficult, okay? Now the first thing that we're going to have to do, oops, my marker's running out on me. Let me get a new marker. The first thing that we're going to have to do is rearrange this equation to solve for the uncertainty in position, which is going to be the delta x that we want to solve for. Okay. Now, on the right of the inequality sign was originally the h over 4 pi. So I'm going to keep that there. And now what I'm going to do is I'm going to divide both sides by this term, basically. Okay. So I divide it on the left, it kind of goes away. But I do it on the right, and then in the denominator down here, I've got a delta u m term that I now need to contend with, okay? So I just did some algebra there to rearrange my variables first. But this allows me to solve for uncertainty in my position now, all right, just directly, basically, okay? And that's kind of what I'm going to intend to do. So what are all these variables? Well, h has not changed. The h is still going to be the Planck's constant, 6.62 times 10 to the minus 34 kilogram meter squared. Okay, not changed. Still, h is a familiar number to us. Okay. Now, what are these other numbers? Well, 4 is just 4. Pi is just pi, right? 3.14. So no big mystery there. Multiply them by each other. But we got some other numbers here we need to contend with. What are these other numbers? Well, I'm going to do m first because that one's the easiest. M in this equation is just mass. But to make the units jive, we can't use grams. We've got to use kilograms, okay? So I need the mass of my particle of interest in kilograms. Now this was this football player. Fortunately, in part 1, we determined his mass was 105.233. So that's no different. So that gets plugged in right there, the mass in kilograms. And the only remaining variable that we need to plug in here is this delta U, which is the uncertainty in the velocity, the uncertainty in the player's velocity. Now, what do we know about that uncertainty? Remember back to the problem we were told 19.8 plus or minus 0.1 miles per hour? That 0.1 miles per hour is that player's velocity uncertainty, right? It's a range of values around the average that we're a little bit uncertain about, all right? So that's the uncertainty. So when we're talking about delta U, or the uncertainty, we're talking about the absolute uncertainty in the velocity of the particle. But again, this has to be in what units? Not miles per hour, but meters per second. So what do we need to do? We need to convert now, fortunately, in part 1, we were introduced to a conversion factor that for every 1 mile per hour corresponds to 0.447 meters per second. So this allows me to basically sort of do this math, okay? It looks like it's going to be 0.0447 meters per second as a result of this calculation. That number then goes over here do my calculation, 0.0447 meters per second. All right, everybody see where I got those terms? All right, so now all we have to do is work our calculator. Let me get my spreadsheet open here so I can do this because I haven't finished this calculation. So we got, all right, 6.62 e to the minus 34 in the numerator. Then we've got equals 4 times pi times 0.0447 times 105.233. So if I do equals 5. Okay, so what I get for the denominator, just to kind of let you follow along so you can work this yourself. So delta x has to be greater than or equal to h, which is this number in the numerator. I just went back to h for a second, so I don't have to write it again. And that's going to be divided by 59.08 is what I see here in the denominator. So h divided by 59.08. Now if I actually put the number back in for h to finish the problem, I get 1.12 times 10 to the minus 35. And that would be in meters, because it's the uncertainty in our position of the football player, okay? All right, so what we've successfully done is use this uncertainty principle to calculate the uncertainty in position of our football player. It's 1 times 10 to the minus 35th meters. Again, vanishingly small, right? So we are really quite certain where that football player is because he's very, very massive, over 100 kilograms. That is a very tiny deBroglie wavelength, okay? But if you start thinking about particles which are very, very, very small, don't have very much mass associated with them, the situation starts to change quite a bit. And the reason why that ultimately is because this delta x, or the uncertainty of the position, kind of grows as this uncertainty gets smaller and smaller, right? So they're kind of like they're inversely proportional to one another to a certain extent. And it's always limited by this ratio. So on the spatial scale of atoms, when we start talking about electrons, these tiny, tiny particles in atoms that are in motion and they have very, very small masses, the uncertainty in their position actually becomes quite large compared to the size of the atom. And to get a feel for this, I think there's an example problem in your book that I encourage you to look back through. But basically, they do a calculation for an electron in an atom, and it basically shows that the uncertainty in the position is larger than the typical size of an atom itself. Okay, so this again has important consequences for how we treat electrons and atoms. We treat them as matter waves in accordance with the deBroglie wavelength. And this Heisenberg principle basically tells us that we can't ever really be certain where an electron is within an atom. We can only describe an electron's position by virtue of probability of finding it in a particular location. Right? And we'll get to that real soon here when we consider atomic orbitals like s and p and d type orbitals, right? So hopefully this was helpful for you.